Okay, let's look at the section 3.2. This section mainly talks about the direct proof, but before we do direct proof, we're going to define even and odd integers. All right, so let's look at that. All right, so let's say n is an integer, and n is even if. All right, so it's divisible by 2, right? So here's how we do it. So say there exists some integer k such that n can be written as multiple of 2. So it's a 2 times k, right? If n is odd, if there exists some integer k such that n is equal to 2k plus 1, right? So those are the definitions of even integers and the odd integers, right? So let's look at the direct proof. As usual, we're trying to prove for all x in S, P of x implies Q of x, right? So here's how we do direct proof. So first, we assume that P of x is true, right? Then try to show that Q of x is also true, right? So let's look at an example, right? So we want to prove that when integer is odd, then n squared plus 1 is even, right? So let's prove that. So here's how we would write the proof. So here's a proof, right? So this is a direct proof, right? Assume that n is odd, right? Then by definition, we know that there exists some integer k such that n can be written as 2k plus 1, right? Which implies that n squared plus 1 can be written as, now n can be written as 2k plus 1, so squared plus 1, right? If you multiply this out, you get the 4k squared plus 4k plus 1 plus 1, so it's going to be plus 2, right? Then we can actually, everyone seems to have 2 in it, factor 2 out. So you have 2 times 2k squared plus 2k plus 1. All right, so therefore, we know that there exists some integer L, right, which is this guy right here. So 2 times integer k squared plus 2 times integer plus 1 is still an integer, such that n squared plus 1 can be written as 2 times that integer L. So therefore, n squared plus 1 is even. Right? That's the proof. Right? That's it. I hope that this was clear.